Okay, so today we're going to study differentiation, and we're going to start off with the basic theorem of differentiation and discuss the power rule, which is not required by the syllabus except the power rule. You don't need to have an understanding of the first principles, but it's highly recommended and it's extremely helpful to know how it works. So without further ado, let's get started. Okay, so here I have a graph and I have a curve drawn on it. And what I'm going to do is I'm going to take this point and I'm going to take this point on the graph. And if I were to draw a line in between these points, what I would get if I took the gradient of this line would be the average rate of change. So the gradient of this line would be the average rate of change. Now remember that gradient is also describing rate of change, but on a curve, unlike a line on a curve, the gradient doesn't remain constant. So that's why we say it's the average rate of change in between these 2 points. So the gradient of this line. And this line is called the secant line. Secant basically means a line that cuts or intersects a curve at 2 points. So it's intersecting it at 2 points. That's why it's called the secant line. So now what I'm going to do is to denote this a bit better, I'm going to zoom in and notice that this is on a different x coordinate, this is on a different x coordinate. So what I'm going to do is I'm going to mark this as x, and I'll say that to get to this point I went out a distance of h. So if I drew a point here, I'll say I went out a distance h on the x-axis to get here. So if I went out a distance h, then this point by that logic will be x plus h, right? So now we're gonna, instead of writing the y coordinates of this as regular y coordinates, we'll write it in terms of f of x, how we write functions, right? So this will be the y coordinate for this will be the y coordinate for this. So I'll write this as f of x, because this is x, and this was x plus h. So the y coordinate of the upper point will be f of x plus h. So now, if I were to write the average rate of change, if I were to write the gradient between these 2 points, using the gradient formula we already have, I can say that m is equal to, we know that y2 minus y1 is equal to x2 over x2 minus x1. M is equal to y2 minus y1 over x2 minus x1. So I'll take the second coordinate as the second point. So y2 will become f of x plus h and minus y1, which is f of x. That's f of x. And I'll divide this by the x's. So x plus h was x2. So we get x plus h, and x was x1, so we get x. So this x and this x are canceling because this is a negative. So we get, for the average rate of change, we get an expression that looks something like this, which is basically f of x plus h minus f of x over h is the average rate of change for the secant line. Now, what I want you to imagine is if I were to shrink this length h infinitely small, but not exactly 0. Like, if I were to shrink this value down as much as possible without actually making it 0, then I can make this point come closer and closer and closer and closer to this point, And eventually, when it becomes so close to this point, I can get the gradient at a single point. Because if h reduces and the points get closer and closer and closer, if this approaches this and gets extremely close, like not actually on there, but so close, then it effectively gives me the gradient of that point. So if I use that logic and I apply that onto the formula I just made, we can see something interesting happen. So the way we denote what I just said of the value getting so close, we said that the difference in lengths between the two coordinates on the x-axis was h, right? So we can write this as limit of h approaching 0, and we write on top of that f of x plus h minus f of x over h. Now notice, it says the limit is h approaching 0. It doesn't say h is equal to 0. The limit does not mean that the value has reached 0. Because notice in this equation, if I were to plug 0 into here, then what would happen is that this would become undefined. That's not possible mathematically. So the trickery we basically use, for lack of a better word, the trick we basically use is that we say that the value is getting closer and closer and closer without saying the value is actually 0. So I'll give a worked example for this, which makes it a bit easier to understand, because this concept in and of itself is kind of mediocre, but when you see the worked example, you kind of see how beautiful the algebra is. So let's suppose that I have a function f of x is equal to x squared, right? So if f of x is equal to x squared, if the function is x squared, then for f of x plus h, I'll write this as x plus h whole squared, and for f of x, I'll write this as x squared, and h remains the constant. And you can't forget to write the limit at the start. It's not necessary to write this each time, I'm pretty sure, but try to write it. So you have the limit here, and this is for the function x squared. So now what I'm going to do is I'm going to expand this. So this is equal to x squared plus 2xh plus h squared minus x squared over h. And notice that x squared and minus x squared are present, so we can cancel these. And in these two terms, I can take h as a common factor. So I can further rewrite this equation to be, I take the h common, I write 2x plus h over h. I can cancel the h's, and now what I'm left with is the limit as h approaches 0 of 2x plus h. And since h is approaching 0 and it's getting so insignificantly small, I can ignore this. And what we get is that 2x is the instantaneous rate of change. Now, when we apply this limit, and we say that limit of h approaching 0, then instead of being the average rate of change, this becomes the instantaneous rate of change. Now, you may be thinking, oh, but we have an x here. The x here is basically because we can plug in any value of x to find the coordinate, find the gradient or the instantaneous rate of change at that point. So this is basically the gradient function. A better way to say it. This is the gradient function. It doesn't give you a constant gradient because on a curve, the gradient isn't constant. So you need a function that describes the gradient, right? So obviously the graph I drew in the start isn't exactly the same as this, but if we were to go back to it, we can see that if I were to shrink h to that insignificantly small value, then what we can do is, at this point, I can draw a tangent, because we know that a tangent is a point where it basically touches the graph at one point, right? So this red line, the gradient of this red line is the instantaneous rate of change, right? Which we call the instantaneous rate of change, right? So the gradient of this line is the instantaneous rate of change, and this, we got this by taking the limit of h approaching 0. So what all of this basically is the derivative. The formula that I just wrote of the limit of h approaching 0 of f of x plus h minus f of x over h, this is the base formula for a derivative. This is how a derivative works. A derivative works. And we can denote a derivative in two separate formats. We have dy by dx. We have dy by dx. And with dy by dx is used in the cases of y. So if I have y is equal to x squared or something, then the derivative of that function is dy by dx is equal to 2x. And if I have it in f of x notation, f of x is equal to x squared or something else, f is equal to x squared, sorry, then I can say that for f of x, I can write this as f prime, which is denoted like this. So if it's f of x, then you can write f prime, which I find to be easier because later on you learn double derivatives, which you add another slash for instead of writing d squared y over dx squared, which you'll understand later. But this is basically the two notations we use for derivatives, and this is the base formula for a derivative. And the limit is not necessary to understand. Like, the informal understanding is useful to know, but the formal definition is not needed by the syllabus. Okay, so for now, for today's video, I'm gonna keep it this short, and I think it's better not to discuss the power rule after this. I'll upload a separate video for the power rule and the chain rule, and I'll try to explain other derivatives as well. But for now, this was enough for today, and I hope that you had a good idea of grasping the concept of how a derivative works, and this is basically how differentiation works, and this is the basics of calculus. So thank you for watching.